Until this point, we've been imagining our atomic lines as being infinitely sharp, so we just have one value for E2 and a single value for E1. In the real world, these are actually more diffuse than that. They're a bit spread out over a range of values. And that's what's shown in this figure down here. So that there is actually a distribution of values, a distribution of values for E2, and similarly there's a distribution of values for E1. So what does that mean? It means that you can go from, for example, an atom which might be sitting with that amount of energy down at the bottom of E1, and it might make a transition up to the top of E2. Or you could have something like an atom sitting at the top of E1, making a transition up to the bottom of E2. So these will have different energies because the gap obviously is different. And so what you'll see is that there is a range of possible values of line width, of frequency. Remember up here we had that the energy of the photon had to be exactly equal to E2 minus E1. And if that wasn't true, then we couldn't get the transition. Now, a range of values, a range of frequencies the photon could have if it wanted to be absorbed, or if we're looking at stimulated emission, if it wants to generate. This is referred to as the transition line width. So it's basically the line width of the transition. And what we're interested in then is if our input photon here, if the signal that's coming in and is going to interact in some way, either through absorption or stimulated emission, if this signal has its own distribution of frequencies, how do we then predict what's going to happen in terms of the strength of the interaction between one distribution of values and the range of possible interaction frequencies? Okay. So each of these is defined by a transition shape, so the shape of that curve, and that shape for the transition, the line shape function is referred to as G, and it's a function of frequency and the center frequency. The center frequency would be from the middle of the distribution for E2 to the middle of the distribution for E1. So the center of that distribution, essentially. So the transition line shape function tells us just what shape does that curve have? Is it a Gaussian shape or something like that? Okay. So our atomic line shape function G, function of frequency and the center frequency, and it describes just a mathematical description of that, the function of that shape. So what kind of curve is it, basically? So if again we have N2 as the total number of atoms in level 2, then what we can say is that there is a distribution of atoms in level 2 which will follow the same sort of line shape function. So the number of atoms per unit frequency is then given by the line shape function times N2. And if we know the line shape function, then we can calculate the number of atoms in level 1 that can absorb in a range between nu and nu plus d nu. Or we can think about it in the number of atoms in level 2, which can emit and give stimulated emission rather than absorption in that same range. So from the equation that we had above, we've got that n of nu d nu is equal to g times n2 d nu. And obviously for as we make approximations, then that line, the d nu value for the input signal is going to become vanishingly small. Now, the definition that we had of the spontaneous emission was that the rate of change of the number of atoms in level 2, dn2 by dt, was minus a2 times n2. But now we have to think about not just the number of atoms in the total number of atoms, but the number of atoms within that frequency range, within the number of atoms per unit frequency that can actually interact, and how quickly do those move. So dn2 by dt is now the number of photons which are spontaneously emitted in between the frequency of nu and nu plus d nu. Okay. We can do the same sort of thing for absorption and stimulated emission. So the line width, line shape of the transition depends on which mechanisms are involved inside the material that cause this distribution of values to occur. Now, this process of it going from having just one single energy, so E2, to a range of energies, having a distribution of energies, is called broadening. So the infinitely perfectly sharp line that we had in our original model has now been broadened out into a range of values, okay, with its own distribution. The type of broadening that you get will be dependent on the type of material. So in gases, for example, you get lifetime broadening, and lifetime broadening is related to the kind of quantum processes which are going on. We don't need to worry about too much about that. It's uncertainty principles involved in that, if you want to look up any more. Collisional broadening, we can obviously think of that as when atoms, molecules, electrons bump into other things and they change the amount of energy that they get. So they get random amounts of kinetic energy, either added or subtracted to the amount of energy that they have. And we've already seen Doppler broadening, so that if the atom is moving away from you, then instead of it being at some central frequency nu naught, it will be at a frequency of nu naught minus delta nu. You know, that is a shift in frequency. So some atoms will be moving at that speed to give you that result. Some will be moving much faster to give you a much bigger result for delta nu. Some will be moving towards you, so that would give you a plus result for delta nu, and so on and so forth. So we have a whole different range of values that are possible because of the Doppler motion, the Brownian motion within the material, and the Doppler shift that those then are seen, to exhibit. In solids, it's a wee bit different. Again, we have lifetime broadening. So that's a kind of basic sort of principle of underlying materials. We have thermal broadening, which is a bit like collisional broadening, so that the phonons in the lattice, or the vibrations within the lattice structure, the solid lattice structure, can give extra little bits of kinetic energy or absorb little bits of kinetic energy. Dipolar broadening, so this is when we get an electric field, for example, if our nearest neighbour is polarised, so that we have our atom as we had before, where we've got a nucleus here and the electron somewhere over there, then that produces its own electric field, and that electric field can actually shift the energy levels up a little bit or down a little bit, depending on the strength of the electric field. So that dipolar broadening is like a nearest neighbours effect. Okay, and then we may have random stress fields because of random inhomogeneities, where you have in the regular lattice of the material suddenly some larger atom or some other impurity within the lattice structure, and that's obviously going to cause all sorts of strains and stresses within the material locally, and that will give you some broadening as well. So all of these types of broadening come into two different classes, and we'll collect them together into homogeneously and inhomogeneously broadened. So we need to understand what those mean. So homogeneous broadening, it means that whatever the broadening mechanism is, it affects every atom in exactly the same way. So irrespective of which atom we look at, the same thing is happening to it. Okay? Every atom sees the same amount of broadening, and the signal applied to the transition has exactly the same effect on all the atoms. So the homogeneous line shape will behave in a uniform way. So let's think about if we had, let's supposing we're looking at absorption instead of emission. Let's supposing we've got all our atoms down in level 1. And I'll just draw it as a straight line just now because it's easier. And we put in so many photons that eventually all of those atoms go up into energy level 2. That means that if we put even more photons in, there's nothing in level 1 to do any absorption. We'll have saturated the material. We'll have moved all of the atoms from level 1 up into level 2. So what does that mean? It means that if we look at the shape of the absorption spectrum, so this is frequency, and this we'll call our absorption, that if we turn up the intensity of the input light here, so if we keep hitting it with more and more photons, then what you'll see happen is that gradually the material is going to absorb less because there are fewer atoms in level 1, and then even less because there are even fewer atoms in level 1 to do the absorption, and then eventually you won't have any absorption at all because there are no atoms left in level 1. They've all been moved up into level 2. And that process is referred to as saturation. Okay, we've basically saturated the system with as much energy as it can take. Okay, we've put in as much energy as it can take. We could do the same thing for stimulated emission. If we think about stimulated emission, then we had all the atoms supposing up in level 2 and none of them in level 1. Then if we put in enough photons, then it will force them more and more of them to make the transition down into level 1, until eventually there are none in level 2 and we don't see any more emission. So it doesn't, whether we're talking about absorption or stimulated emission, we have the same sort of process of saturation. So mechanisms that give you homogeneously broadened lines, lifetime broadening, collisional broadening, dipolar and thermal broadening, they effectively act in a similar way to, or in a same way to every atom within the collection. The distribution for our line shape function is given by a Lorentzian. Okay, and so this is our Lorentzian function here, and you can see it depends on the center frequency and it depends on the value of nu and in terms of its line width delta nu. Okay, so it's the center frequency, delta nu is the full width at half maximum. And you'll see that in some textbooks as FWHM. And delta nu over 2 pi guarantees that area under that curve equals 1. So if we integrate over all frequencies, g of nu, that should be equal to 1. Okay. Where the frequency can go from 0 Hz up to infinity. Why is it normalized? It's normalized because this is also a measure of probability, and the probability of something happening between, if something's going to happen, then it must be between 0 and infinity. So the probability of it being somewhere between 0 and infinity must be 1 if we integrate over all possibilities. Okay. The peak value for this curve, so the maximum value it can have, is when nu is equal to nu naught. So that's when nu equals nu naught in equation 22. And we end up with a peak value of 2 over pi times delta nu. So what you'll see here is that the peak value, the maximum value that distribution can have, the peak value here is inversely proportional to the line width. Okay, so if I have a narrower line width, it means that my peak value will be higher. So here's a graph of two distributions, a Lorentzian distribution, a Gaussian. We'll see why I'm talking about Gaussian distributions in a second. Given for the same line width, and what we'll see is that the Lorentzian line is has much wider shoulders than the Gaussian. The Gaussian is much narrower for the same value of delta nu. Okay. So in homogeneous broadening, all of the atoms are acted upon in the same way. In homogeneous broadening, surprise, surprise, it means that the atoms are being acted upon on an individual basis. Okay. As well as giving you broadening, they also tend to shift the center frequency of the transition. So if you think of things like Doppler broadening, the frequency should be at some center frequency nu naught, but it isn't. It's because it's moving away from us or towards us, we see the frequency at a different value. It's shifted up or down depending on the direction. And so what we have is lots of atoms or ions or molecules, depending on what the material is made of, and they're all doing their own thing. They're all moving in their own direction at their own speed, and a v for velocity. And so there's no obvious kind of collective behaviour that you see. What you'll see is the average behaviour, so that when you add all of those individual parts together, what you'll get is a Gaussian distribution. So what I want to show is that for some atoms, let's just think about Doppler broadening for the moment, some atoms will be at lower frequencies, so they'll be moving away from you, and they'll be moving away from you very, very quickly, but not many of them. Most of the atoms will be around about the center frequency and only shifted by a small amount, so that we get nu naught here. And then some of the atoms will be moving towards you very quickly, and so they'll give you a distribution somewhere around about there. So when we add all of these together and we integrate, well, we convolute rather, all of them, then we get this Gaussian distribution, this overall Gaussian distribution. Now, if you remember, that's terribly drawn, so I apologise for that. If you remember what happened with the inhomogeneously broadened, the homogeneously broadened, I do apologise, materials, when we thought about saturation, then again, Here's E2 and E1. If I apply my signal at that, let's not make it that point, let's make it this point here, then it's only these atoms which are around about that point that can interact with it. Okay, so these atoms over here, that's their transition. So remember, if the delta E is not equal to H times nu, we don't get a transition. If it's not equal to the gap, we don't see anything. So if we apply a frequency here at nu, then the atoms which are doing this sort of transition don't care what's happening over here, because they won't interact with it because of this this condition. It's only atoms which are around about the frequency that we apply that will actually do any interaction. So it means that when we apply this idea of having lots and lots and lots and lots and lots of atoms in level 2, and we're putting in more and more light to get more and more stimulated emission, then it will saturate in a much different way. What will happen is that only the atoms in the sort of neighbourhood of our signal, the input signal, nu, are going to interact. So if we can scroll down, what you'll see is that the rest of the collection doesn't really care where you apply your signals. This is our value for our input signal, nu s. And it's only atoms that can interact with that signal, or around about that signal, that will start to saturate. And what will happen is that as we apply more and more, then it will come lower, and then even more light and lower, until eventually you get full saturation and it goes through zero, and we don't see any absorption or stimulated emission. Okay. So if we apply our super intense signal to look at what happens during saturation, then it's only the atoms which have a frequency which is close to the signal frequency, only the atoms that can interact around about that frequency, that will actually interact with the energy, with the light coming in. The rest of them won't. And so we get this kind of hole burning behaviour that we see in the graph below. So Doppler is an obvious one. Random inhomogeneity is also an obvious one, because they obviously act individually on individual atoms. We have a Gaussian distribution, so an e to the minus something squared over a constant is our standard Gaussian distribution. We have our line width again, and again we have a normalizing factor at the front here, so that when we integrate the area under that curve again, it equals 1. And if again we say that nu is equal to nu naught, if we look at the peak value, then this all disappears to give us e to the 0, which is 1, and leaves us with our constant at the front for our peak value. And again, it's inversely proportional to the line width, so the broader the line, the smaller the peak.